All right, so next, I want to discuss a bit specifically what this might look like in some special cases, particularly in the case of a linear threshold network and some geometric methods that will allow us to produce some statements for the case of neural networks. All right, so linear threshold networks. So what is a linear threshold network? This is a neural network which has an activation function that is a threshold function. Produces 0 or 1 as an output. Let's say first, what is a feed-forward network? That is described by a directed graph with nodes enumerated in such a way that each node has incoming edges only from lower nodes. The number of layers of the network is the longest path from input to output. And and then for every node, we're gonna basically apply an affine function of all the variables that have incoming edges, and then we apply the activation function. So the activation function for a linear threshold network will be the following. Is this function that maps its argument to 1 if this affine function attains a non-negative value and 0 otherwise. All right, so each neuron in this feed-forward network is going to apply such an affine function and then basically output the sign of the, or kind of the Heaviside step function for what comes out of that affine function. Right, so now for the parameters of the network are going to be all the coefficients of these affine functions in all of the computational units in the network. All right, so and for this kind of network, we can obtain this type of bound for the growth function and for the least dimension. So let's say that H is the class of functions that is computed by a linear threshold network, and we're going to say, let's look at a network that has k computational units and a total of capital W weights. So we take multiple layers and all the computational units that are containing all of those layers. Together they are k, and W is the total number of arrows that come into all those units, plus the units themselves if we have this intercept for the affine functions. Then we have this type of bound. So the growth function for that hypothesis class is bounded above like this. So nk divided by W to the power W. So here E is just the Euler constant. And well, n is the number of data points, and k is the number of computational units, W is the number of weights and biases or thresholds. And from this, one can already derive what the least dimension would be. So recall the least dimension is going to be the value of m, the largest value of m for which the growth function is 2 to the m. And so you can verify when this thing is going to be most for 1m, this thing is going to be 2 to the m, and then obtain this sort of a bound for the least dimension. So it's kind of W log k. W log k. Okay, so now, how would we go about showing that this is true? So we would need to kind of compute the number of dichotomies that we can implement with such a network. Is this difficult? Okay, first maybe, so this is essentially tight. We can essentially obtain a matching lower bound. For the proof, it is not too difficult, and actually one can prove this using a relatively generous approach. Generous in the sense that, so we already computed, recall the growth function for a simple perceptron, right? A simple perceptron is just a single neuron that is a linear threshold neuron. Now we're kind of putting a lot of those neurons together to create this big network. what we can do is say, all right, so the number of dichotomies of the entire network is going to be bounded by the product of the number of dichotomies of all the individual neurons. And we need to do a good counting for that, and maybe we're going to obtain this result. It goes like this. Let's say that S is the number of input patterns. Let's say we have M of them, input data points. And then let's call a state of the network the assignments of weights and thresholds. Basically, just fix the parameters. And let's now look at this of L of S, which is going to be the number of states that compute different functions on that input data set S up to the nth unit of the network. So maybe the network has these several input neurons, and we are connecting them to some other neurons like that. I guess we could have something like this. And these are enumerated. And maybe this is the output. And all of these together are the input. And maybe now we want to say how many dichotomies do we compute over the input data set up to a particular neuron. Let's say this one is the L one. So let's put the L in the input pattern. Input patterns. So how many different dichotomies can we compute up to here? Why am I saying that? Is because we're saying the maximum number of different parameter choices that will give us different functions over that input data. And now, certainly the number of dichotomies of the entire network is going to be less than the number of different functions that we compute or that we observe on the network over up till the last layer. And right, so then what we can try to do is basically compute a bound on this quantity in order to bound the number of dichotomies. So what we do, we can consider the parameters up to a certain unit, let's say for neuron, the neuron L-1, and the thresholds up to the neuron. And then, yeah, so we have actually that this dimension of a particular neuron, which is a linear threshold neuron, or a linear threshold unit. That's the one we computed in the past session. But that one is equal to essentially the number of arguments, the number of inputs, plus 1. So for the simple perception over n dimensions, the DC dimension plus n plus 1. And so here we can do something similar. Let's say if we were to be looking at this guy over here, so we would have this number of inputs plus 1, and that's the total number of that's the maximum number of input patterns that we can chatter. And from that, we had a bound on the growth function, and the bound the growth function was something like this one, m divided by d to the power d. If we have d arguments for that neuron, let's say for the first neuron, so we will obtain something like this. And now let's say that we go to one neuron farther up. So we go to the next neuron over here, and now we want to know, how many patterns can we compute up to here. And it's going to be a product, or it's going to be bounded above by the product of the number of functions we compute up to here, plus the number of functions we can compute over here for this second part. And for the second part, so this is essentially the bound that we have for the growth function, and then we have the bound for the first part of the network. So thus all together give us an upper bound. All right, so then if we iterate this, we end up getting a product over all the neurons of the network. So from 1 to k, the total number of neurons. For each neuron, we have the corresponding bound on the growth function, and that's the bound for the total number of functions that we can compute over all the neurons of the network, and that's an upper bound on the growth function. Now we can manipulate this expression a little bit by taking a logarithm and dividing by w, and then adding some constants, so both to the left and right hand side. And if we do that, we obtain the following expression. There's some kind of manipulations here. Gives us this thing. And now, so why are we doing this, or why is this useful? The reason is that the statement that I showed you is a very general statement. It's valid for any architecture. Like, it doesn't have to be this one. It could have been one where the computational elements are arranged in a different form, so long as you have the same number of computational elements. And so somehow we need to obtain a result that is flexible enough to account for all those different architectures. And so we somehow want to obtain an upper bound over that flexibility. And to do that, so we're going to take this upper bound and try to maximize that. So we need to maximize essentially over the number of arguments of each of the neurons in the network to try to obtain the largest possible value of this right-hand side. And now that we have rewritten the whole thing in this way, this actually is the expression of an entropy of a discrete distribution. So a discrete distribution would be the distribution with k elementary outcomes, each of them with probability dl divided by capital W, because capital W is the sum of all those dl's. So we have here essentially the probability of elementary event L times log of 1 over elementary event L. So that's the entropy, and we know what is the maximum value of the entropy, so we can maximize this. So maximum value of the entropy is obtained for the uniform Pauli distribution. That would be when all of the dl's are equal. They would be equal to capital W divided by k. And the entropy would be then just log k. So we obtain here as an upper bound, just log k. And then we just rearrange to have an expression bounding the growth function, and it comes out to be like this. So previously we had this bound. This depends on dl, but the theorem that we had written was not depending on dl. So now we have cleared that dl because we have maximized over all possible choices of the dl's. And we get this final upper bound, which is what we had in the theory. All right. And then to show the DC dimension, we just evaluate when this stops being equal to 2a. Questions? Okay. So in some sense, we have formulated a theorem here that is very simple, is very easy to read, but in reality, we're able to be more precise if you have a particular network in mind. You say, I want to consider a very special network, not just any network with a total of k neurons. So then you could use, instead of using this bound, you can use this one more specifically. That is a bit more accurate. All right, so next, we want to look at lower bounds. And for lower bounds, we need to show that some particular architecture, some particular hypothesis class represented by the network can represent a certain number of dichotomies. And we can consider special cases and try to bound that number from below. So one special case would be a linear threshold network with 2 layers. And we're going to consider the case when these are fully connected between adjacent layers. So the neuron in one particular layer receives connections from all the neurons in the previous layer. And here we may consider binary inputs for simplicity and to start. So our input data is going to be binary vectors in n dimensions. And then we have k computational units in the first layer and one single output unit. And so in this case, we can obtain this lower bound for the DC dimension, that is n times k plus 1. And so for this particular structure, that turns out to be equal to or bigger than or equal to W, where W is the total number of weights and biases and thresholds. Yeah. So this is not quite matching the upper bound that we had in the previous statement. The upper bound that we had was W log k, right? And now we have just W, but it's getting close. One reason why we maybe don't need to be very disappointed is because this is a very special type of network that we're looking at. It only has 2 layers, and it is operating over binary inputs, whereas the upper bound is for any network which has a certain number of neurons, but it could be deep. So it could be that a deep network is actually capable of representing more functions than the more shallow network. And also, if we allow the inputs to be non-binary, that also allows us to represent more functions. All right, how do we prove this? Easy or difficult? So one good thing about lower bounds is that we can sort of obtain them by construction. We need to show that we can implement a certain number of functions. So we can try to construct them essentially by hand. All right, so here's a possible proof. This uses some coding theory, which I think is interesting. Some error correcting codes. The error correcting codes for binary inputs. So recall that we're dealing here with binary data, right? So what's going to be the idea is that you can think of a binary vector with n components, or the set of binary vectors with n components. You can think of them as being the vertices of a cube, n-dimensional cube. And what we're going to want to do is try to take different corners of that cube and try to do computations on all of those corners separately, and then aggregate them together in the subsequent layer of the network. And yeah, but how do we do that? So first we need to figure out how many corners are there, and how many corners are there that are separate from each other. And that's where the error correcting codes come, because so you can think of binary strings or binary vectors that are separate from each other by at least having distance 3, and the corners are disjoint, overlap. Right, and so basically, how many corners does a cube have, a binary cube? So the exact number is actually not known in general, but we have lower bounds. It's one of those interesting things about binary cubes that is not fully known. But you know, the Gilbert-Bashamov bound is one of those. It tells us that the number of elements in the cube that have coming distance at least 3 from each other, the largest set of elements with that property is at least this big. 2 to the power n plus 1 divided by something, n squared plus n plus 2. And you can imagine every corner would consist of one vector and all its neighbors. How many neighbors does a binary vector have? Dimension n, it has n neighbors. So you can have n plus 1 elements in such a little ball or neighborhood. And you could be tempted to say, all right, so that means that I could have as many as 2 to the n divided by n plus 1 disjoint corners or neighborhoods in such a binary cube. And yeah, this is getting close to that, and maybe not quite, but you know, but it's a pretty good bound. All right, so then what do we do? Next, what we're going to do is for each of those neighborhoods, we're going to run some computation with an inner threshold unit or neuron. Maybe I'll show you an illustration for that in just a second. But so essentially, every neuron can run a computation on that neighborhood, and basically output 1 if and only if some particular configuration is happening over that particular neighborhood. And we have the next layer only output 1 if all of the previous computational units actually outputted 1. Right, so it looks like this. So maybe this is the input space, the space of binary vectors, here for 3 dimensions. And these are going to be the neurons in the first computational layer. And we're going to see that, so maybe this is the output. This is the first neuron in that layer, could take value 0 or 1. And this is the second neuron, it could take value 0 or 1. So that's what gives us the square. And so maybe for the first neuron, we consider here the corner or the neighborhood that we look at is the one that is centered at this point Ci, and all the adjacent points are this one, and this one down here. So our three neighbors for three dimensions. And the idea of how to construct this is that we call that a linear threshold function. Is essentially defining a hyperplane, and it's going to assign value 1 to everything on one side and value 0 to everything on the other side. So what we're trying to do here is place that hyperplane precisely such that it cuts through all the points that are adjacent to CI. And from that, geometrically, you can imagine that you can perturb that hyperplane ever so slightly to have either of the points fall either on one side or the other. So that sort of tells you that you can express any dichotomy over those points that are adjacent to the CI. All right, so in this particular case, we would be mapping maybe this point X, this corner in here, is being mapped to this particular location. So where the first neuron took value 1, if we perturb the hyperplane a little bit, now it's going to be falling underneath the hyperplane, and so this output is going to be now 0 as opposed to 1. The last neuron of the network is just going to correspond to some hyperplane cutting through the values that we have in the first layer, and so maybe it's this hyperplane is going to assign value 1 only to the points that are to this single point, which is happening when the outputs are 1. Okay. All right, so what does this tell us is that the total number of computations that we can do in here is going to be equal to the product of all the elements of these neighborhoods. And how many elements do we have in all those neighborhoods? We have n in every neighborhood, and we have k neighborhoods. So we get nk. And right, so this is provided that k is not much bigger than n. So we have this bound, k has to be at most equal to this bound that we have from the Gilbert-Rashad model. So because that many disjoint neighborhoods you can find in those input patterns. Well, that gives us the result. Questions? Okay. Next, maybe this is a remark that could be interesting. So you could ask, how big a neural network do you need to be able to represent any possible dichotomy over binary vectors of length n? And that's something that people have studied in the past, and it's quite interesting. So let's look at, let's define HC to be the smallest number of computational units that you need in a network, so that you will be able to represent the function that is activated on the set C. So it's value 1 of C and value 0 otherwise. So let's say you want to be able to indicate or output value 1 just to the elements in the set C. So how big a neural network do you need to represent that function? We denote that by HC. We can also then define H sub n to be the maximum over C. So that would mean that you have a network of size H sub n, and you will be able to represent any classification over the binary vectors length n. So this make the result by Wenzel, Maya, and Tasseman that obtains lower and upper bounds for that. So it says that if the network has at least or more than 2 to the power n half, then that's sufficient, and you're never going to need more than 2 to the n divided by n plus 2. So you want to say, you want to memorize arbitrary binary functions over binary input data. How big a network do you need? This is not a statement like that. There are more recent results. This is also a result by Waldi and Bershinin on the capacity of linear threshold networks that also investigate similar questions and obtain bounds of that sort. There are more recent results as well in the case of memorization for neural networks for classification. So this is, it's still a topic of investigation. Let's say the classic question maybe started being investigated like in the 40s. Earlier. Yeah.
So in this bound, do we expect the upper bound to be sharper than the lower bound?
That's a great question. I'm not 100% sure. Or I don't know at this point.
Because I guess just like dimension counting, like counting the number of parameters, it seems like it would be closer to 2 to the n.
I mean, the right-hand side looks certainly more natural, and you would anticipate that, you know, it would be more like that than the left-hand side. But I don't want to presume to know the answer at this point. And great question. Yeah, it might be worthwhile to check out, you know, some of these references in regard to this specific question. But this work is kind of more general, considering deep networks. And some of these other works that I mentioned about memorization, I don't think they have emphasized too much this particular question. So, but maybe some of these articles, one can still instantiate them and see what they signify for this particular problem. Yeah, I can say more about that maybe afterwards. So that's okay. All right, so then next we can also try and see whether we can obtain other lower bounds that with a higher value if we allow ourselves to take maybe a deeper network or networks that operate on real inputs and not on binary inputs. So because we have seen that the VC dimension of a network is bounded above essentially by W of W, but so far the lower bound that we had was linear. And so this is a result here that produces a superlinear VC dimension lower bound. And it, you know, maybe conceptually what that means is that every single parameter or every edge can add more than a constant to the VC dimension. If we were to be adding a constant, then we would have something that is linear and to 200 parameters. And this result says that if you take a network with 3 layers and W parameters, and then still for binary inputs, one can obtain, so there exists a 3-layer feed-forward network which has this lower bound for the VC dimensions, W log K. And K here is the number of computational units. All right, then it is actually also possible to obtain a superlinear bound, a lower bound for the case of a 2-layer network, provided that the inputs are real rather than binary. So result by Sakurai that in this case now 2-layer linear threshold network, but real inputs and K computational units, then we obtain this type of lower bound nk times log K, which is essentially W log K. Here again, W is the number of weights and thresholds. So that's interesting. That's good. A couple of remarks here. First, yeah.
Sorry, I just had a question. Could you explain a little bit more about why adding on the slide right before this one, why adding an edge gives you more than constant? A little bit more.
Oh, here.
Yeah.
Yeah, right. Well, you know, we're producing a lower bound on the VC dimension, and if this happen to be linear, then if we only have a linear bound, then that means that every parameter that you add, so linear would mean that you have a constant C times W being the VC dimension. That means for every parameter you add, you are adding at most C to the VC dimension. So if you wanted to, or if you can show that it is actually superlinear, that means that you have to be adding more than just a constant C.
So yeah, I guess like how would adding a single edge do more than that?
Well, this is the implication of the statement, because the statement is telling us that, you know, we can find a neural network that has a VC dimension that grows superlinearly in the number of parameters. So the implication of that is that every single parameter that you added had to contribute more than a constant to the VC dimension. Yeah, okay. All right, so a couple of remarks. Yeah, so these statements gives us a lower and upper bounds of the form W log W, and or within some constants, and so this is asymptotically tied. Then for networks of fixed depth, I should mention that as the number of parameters increases, the DC dimension cannot grow this fast without additional conditions on the architecture. So especially for the lower bound, we said there exists a network, there exists a neural network architecture such that this is true. And so, but we cannot just say that it's going to be valid for any neural network architecture. So an example is that if you have a network which has first layer of some size, K1, and the next layer is enormously large. So at some point, this next layer is not going to be able to contribute any further because everything that you observe on the first layer are going to be binary vectors, and there are only so many binary functions that we can compute. Like from binary inputs to binary outputs, there's only so many functions that exist, and so adding more computational power afterwards is going to end up giving you duplicates. So that's just an illustration of that. All right, so I'm going to stop here and we continue after. Oh, yes, please.
Yeah, so maybe one question about theorem 3. So I remember in theorem 3 we have a upper bound of the growth function, right? And it looks like the upper bound is is achieved when each layer has same width. Is that actually suggesting in practice we should use like the same width to increase the size of our function class?
Yeah, that's a suggestion. At least for this is an upper bound, we call that. So you're saying the same number of inputs per neuron. Yeah. But this is an upper bound, and it's a sort of a generous upper bound in the way that we constructed it, because we're multiplying the DC dimensions essentially of all the computational units. One would need to, if you wanted to argue that you're going to be able to have, well, an upper bound means that and this is like this. So you're not going to be able to do better than this for a particular architecture. So if you want to have the chance of being able to do better than that,
it may not be that big actually. It's just not.
Right. But if you want to have the chance to be able to do that, then yes, you would need to distribute the parameters evenly across the different nodes. Yeah. So in particular, if you have some kind of bottlenecks or something like that, you might actually end up damaging the flexibility for the bound.
Right, let's think of the
Little bit of detail how we could go about computing these quantities for different parametric models and including neural networks. Maybe some other as well. So the general idea is to try and think about the strategy that we did for the simple perceptron. So for the simple perceptron, recall that what we did was, in order to estimate the growth function, we looked at the subdivision of the parameter space. So we partitioned the parameter space into regions, and each of those regions corresponds to a particular dichotomy. And now we can try to do something similar for a more general hypothesis class. So, and subdivide the parameter space, count the number of regions, and that gives us the growth function. For that, we can consider this particular class. It is called a K combination of signs of some function class f. And what is that going to be? We're going to take some binary function that maps from k binary values to 0, 1. Let's say we have some kind of a committee, and for the committee, each of the committee members takes a vote, and then that pattern of votes, we map it to a final decision. And what are these committee members are going to be elements in this class F. And it's going to be such that the class, this K combination of signs of F, are going to be the functions that are expressed as this function G, and composed with all the votes of the different committee members. All right, but so and then the committee member could be whatever. At this point, we haven't said anything much about it yet. It's just going to be some real value function. I have written that here depending on both the parameter. So we'll have a parameter and we'll have an input space. Right? right? So, but we're gonna pick those, this class F to be continuous in the parameters. For any choice of the input data point, we're gonna have a function that is continuous in the parameters. That's the requirement. All right, so then how are we gonna construct those subdivisions of the parameter space? And recall the idea that we had for the simple perceptron was to look at these hyperplanes, and the hyperplanes, they arose as the boundary between when we are classifying a particular data point as being in the positive class or in the negative class. And that hyperplane, what is that? That's something that you might call some sort of an indecision surface. And so it's going to be essentially the set of zeros for, say you take your function and you evaluate it at a particular input data point, and you look at all the parameters for which that output is undecided about the class that you should assign to that particular input data point. So each of those surfaces is going to be essentially the zero of the function over the parameters. So when we look at all the parameters where the function vanishes, evaluate that the particular input data point I, the ith input data point. We can call that Ci, some hypersurface in the parameter space. We're going to need a technical condition here for this whole discussion to work, and that's going to be that we take k, we're going to say that k differential functions have a regular zero set intersections if, when we look at these surfaces, they intersect nicely. All right, so what that means is that we look at any point in the intersection of those surfaces. So let's say this intersection of the Cij's, or j from 1 to L, and take a point in there, and now we want that the gradients of those functions at the point are linearly independent. All right, so that's going to be a condition. We're going to call that as this set of functions having regular zero set intersections. I'm going to show you a picture.
What guarantees that this is like a surface?
This guarantees that the surfaces intersect nicely. So let's say that this was one of the surfaces, and we want that the other one intersects nicely like that.
No, I mean the Ci. How do you know it's not a disjoint set or something?
Oh, it can be disjoints. I mean, it's a surface that can have multiple components.
Okay.
So it could be.
It doesn't split the space.
It will split the space potentially into many different connected elements. So one of those C's could be like this, and so you would get 1, 2, 3, 4 different connected components. But it will have 4-dimensional one, so it's going to be a hypersurface even if it is not connected. In reality, and that's also something that if you're interested, we can talk more about after the session. You could have functions here that are not necessarily smooth, and where maybe the surfaces they're going to be kind of piecewise linear, something like this. And piecewise linear surfaces, they can be of interest in some particular models like Renwu neural networks or Maxwell neural networks. And there are a couple of very interesting things that happen in those cases. And let's say a remark in a moment. All right, so one implication of this definition would be that each of these functions, each of the fi's will have a non-vanishing gradient at its zeros, and this is the condition that we need to say that this is in fact going to be a codimension 1 hypersurface. If we had a vanishing gradient, then the set of zeros could have a non-well-defined dimension, or could have some dimension different from codimension 1. And also, an implication is that if we intersect d plus 1 of these functions, or of the zeros of those functions, then that is going to be empty, the intersection of d plus 1. Because we cannot have d plus 1 gradients that are linearly independent if they live in RD. So, but for generic cases, of course, if you intersect 2 surfaces in R2, generically they may intersect, but you're not going to have generically 3 surfaces intersecting at one point. So that never happens. So it's going to be excluded by this condition. Okay, then, okay, this was the example. So I have put here 3 curves, and each of the curves is the set of zeros of one function. So maybe this is f1, and we've got all the zeros of f1, and then this is maybe this parabola. Set 2 is the line, and set 3 is this one. And so here, if we evaluate just the intersection of, say, set 3 just by itself, then we may look at the gradient of f3 at some particular point in that 0 set, and maybe that's this gradient. So the gradient is not 0, and so that would be consistent with our definition. Over here, the intersection of set 2 and set 3 is this point, and we look at the gradients of f3 and f2, and maybe they point like that. They are linearly independent, so that's nice. So the gradient is going to be orthogonal to the surface, of course. But in this case, like the intersection of set 1 and set 2, the 2 gradients are kind of collinear, so they are not linearly independent, and that would violate the definition. And all right, so you can sort of tell that. So when you have this regularity condition given, the intersections are sort of proper, and so you can actually do a counting with the intersections. Okay, next. There is this definition that we're going to use, and what it says is that, so we're going to consider a set of functions g, and we're going to say that it has a solution set components bound B if for any k less than or equal to d, and any k functions from that class, which have regular 0 set intersections, we have that the number of connected components of the intersection, these 0 sets, is at most b, meaning that so we have one of those guys, and maybe we intersect here 2 of the 0 sets, and here the intersection is this set. Consists of 2 points, so it has 2 connected components. The question is, how many connected components could we get? Like if we had something like this, we intersect them, we will get here a lot of points, so the number of connected components will be higher. So depending on how complicated the 0 sets are, so the number of connected components of the intersections can go up. So this is going to allow us sort of to control or measure the complexity of those functions, and it's going to, the results that we obtain are going to depend on this sort of bound. So if you imagine that these are polynomials of a certain degree, then the number of connected components of the intersections is going to be bounded depending on the degree of those polynomials. Right. Okay. Simple example, with a simple perceptron, this corresponds to the case where we have a k equals 1 combination of signs of f, with f being just affine functions or affine linear functions. So compute an affine function, and then in this case, each fi, so if we were to evaluate, so if we call these fi's, we want to define them as being the computation over the parameters for a fixed input data point. So we fix, say, a data point xi, and we still have now as an argument the parameters of the simple perceptron. And in that case, the 0 set would be just the parameters, so that this fi is equal to 0. That's just when does this evaluate to 0 for a particular choice of x, xi. There's going to be you can write it in this way, so it's a linear equation in A, the parameter, and so that's a hyperplane. That's what we had previously, and so we're going to have one hyperplane for every data point of the data set, and right. So and then we can ask, do they intersect regularly, and what is the solution set component bound? So for hyperplanes, if they intersect regularly, that means that all the normal components are kind of linearly independent. And then oh yeah, so the intersection of hyperplanes is going to be a linear space or an affine space, and that certainly has just one connected component. So therefore, the solution set components bound for this particular example would be b equals 1. We only have one connected component. All right. Next, so we're going to be looking at this result. So this is the type of statement that we can obtain under these definitions. So let's say that we take a function class f, that we we're thinking of it as mapping from parameters and input to some real number. And we're going to assume that this is in CD, and we are going to assume that this is closed on the addition of constants. Then this has a solution set. Let's assume also that it has a solution set component bound B. And now we define our hypothesis class as the K combinations of signs of this guy. As we had it, we had a committee of K elements from this class F. Then what is the growth function of this class? So the growth function of this class is going to be bounded above by B, which is bound on the solution set components, times this binomial sum, and we can upper bound the binomial sum just by this expression here. So this is going to be an upper bound for the growth function of this class. Right, so that's pretty nice because maybe this allows us to cover very big diversity of candidate models or neural networks based on some relatively general properties like the solution set components bound. So what we have here, okay, this goes with K divided by D to the power D, where D is the number of parameters, so it's the dimension of the parameters. Okay. How are we going to prove this? So actually, the way first we're going to say that this is the strategy. The strategy literally is that we're going to consider all these zero sets as being these indecision surfaces. So for every one of the committee members, we're going to fix a different input data point, and we evaluate this now as a function of the parameter. So we look at a function that has the parameter to the output on the input data point xj for the ith committee member, and we can consider the zero sets for this, and we consider all of them. So we have K committee members and M data points, and now so this results in this collection of hypersurfaces, and we're gonna be splitting the space of parameters by those hypersurfaces. So let's look at the parameter space. We subtract all of those hypersurfaces, and that gives us a bunch of connected components, and each of those connected components corresponds to a dichotomy. So that's an upper bound in the total number of dichotomies for the growth function of this class. So it's kind of a strategy. So now what we need to do is basically, this has become now sort of this combinatorial geometric problem, which is to estimate the number of connected components that are left in the parameter space once we remove those hypersurfaces. All right, so do we need a proof for this? Because I already explained this in words, and so every one of the cells corresponds to a dichotomy, and because each of these surfaces, so if you wanted to have, if you wanted to change the dichotomy, you're essentially going to have one of the outputs of one of the committee members switch the output in one input data point, in at least one data point. And so that means you have to move from one side of the surface to the other side of the surface. And so the different cells correspond to those dichotomies and so on. All right. Yeah, so this is just providing a little bit of explanation for that. And then there's a little bit of work that needs to be done in the sense that what happens if you have parameters that are sitting in some particular intersection or some zero set, and you can actually argue that we need to consider these different connected components because we can perturb them using the fact that our function class contains constant functions. All right, or we can argue, that we can obtain regular zero set intersections. That the case when we don't have regular zero set intersections is kind of a measure zero situation. Next, what we need to do is bound the number of regions that is defined by such an arrangement of zero sets or surfaces. And one approach for doing that, so we introduced the solution set component bound. So now we want to be able to relate that to some solution set component bound. And the way that works is this very nice relationship. What it says is that we can relate the number of cells to the number of connected components of the intersections of the surfaces. It goes like this. So we have k differentiable functions, and let's say they have regular zero set intersections, then the number of connected components that we get in that parameter space is bounded above by some sum of the number of connected components of the intersections of those surfaces. It's pretty neat. I'm going to show you a figure in just a moment. And this sum is running over all possible intersections that you could look at. So we take, for any subset of surfaces, we consider the intersection. Then we look at how many connected components that intersection has, and we sum all of this together. That's an upper bound for that guy. So this formula looks familiar from somewhere. From where?
From the book. Yeah, we got
Okay.
it.
No, this is familiar maybe for people who have done Möbius functions and Möbius inversion. So for functionally ordered sets, for posets and lattices. Okay. All right, here's an example. We have here 3 surfaces. And it's from before, and we see the cells here is 1, 2, 3, 4, 5, 6, 7, 8 different cells. And now, is this related to the number of connected components of intersections? Okay, we can look at first the intersection. The empty intersection is the whole space, so that's the first element. Then we can look at the intersections of the surfaces, by themselves. The first one, just by itself, has a single connected component. In this case, the second one, single connected component. The third one. Then let's say we intersect the first and the second one, so that now this intersection has 2 connected components. So we add a 2 in here. And then the intersection of, I guess, the second and the third one is just 1 connected component, and the last one also just 1 connected component. So, and miraculously, this 8 is indeed upper bounded by this quantity, and in fact, in this case, they both are equal. So 8 is equal to 8, so that's quite nice. So we can therefore focus our efforts now into looking at how many connected components do we get in those intersections. All right, now in order to prove this, so it's kind of a direct proof, let's say, on we're going to use 2 lemmas. The first one is this, and it says something very elementary, but it's very fundamental. And let's say that we have it's k functions, and for each of them we define an S set that is going to be either a 0 set for that function, or it's going to be a set of points where the function is not 0. And let's say we look at a connected component of the intersection of the first k minus 1 of those sets S. And then we look at a connected component of the intersection of that set C with the last surface. And now we want to remove that C prime from C, and this has at most 2 connected components. That's the thing. It's a lot of words. Maybe more intuitively, all that I'm saying is that if you have a connected set and you remove from it another connected set, you're going to get at most 2 connected sets. So it's sufficiently clear intuitively. I think I have a figure. So the set C here would be the intersection of, let's say, S1 and S2. So S1 is some kind of take shift and let's do another one. We intersect with this curve, and in this case, well, there is a single connected component here, so that could be our set C. And let's say now we intersect that with the third surface, S3, and let's say it intersects at these 2 points. And C prime is going to be one of the connected components. So let's say C prime is just the point here to the left. And now we're going to remove that C prime, that single dot from C, and that's going to have indeed at most 2 connected components. It has 2 connected components. We have split that set into 2 connected sets. And it's not going to be more than that. And this is interesting and it's fundamental because, you know, in some other settings, you could imagine that, say you start with a set like this, and let's say this, if this happened to be C and C prime is a connected set that looks like that, then of course, if you were to remove this C prime from C, you would actually get 3 connected components. So that's not happening here because we're looking at sort of regular surfaces. This is not a regular surface because this has kind of this funny behavior here. So that's what I'm saying, you know, this is kind of very naive, but it's very fundamental, and it can actually break, especially if you are doing computations with some piecewise linear functions that are more general. You know, these sets may actually have this sort of form, and then, you know, subtracting or removing those elements can give you more than just 2 pieces. These would need to be adjusted and modified in these groups, which is possible. All right. Next, the next lemma that is used in order to obtain that result is an induction on the number of regions, and it's similar to a sweeping hyperplane method that we use for the simple perceptron. The sweep hyperplane method. You remember what we did? I'm going to repeat the drawing just for making that. Maybe you recall that. So the drawing that we had was something like this. So we have an arrangement of 2 surfaces, and we're adding a third surface, and we want to know how many regions do we get in total. And we said that's going to be the number of regions we had at the beginning plus the number of regions that we get in a new surface. And we're going to do something very similar over here. So we're going to have here to the left-hand side is how many connected components we get when we remove the surfaces. And the statement is that that's going to be bounded from above by whatever we had when we only remove b minus 1 surfaces plus something else, which is take the bth surface and remove from it the b minus 1 surfaces. So it's like this picture, pretty much the same, just that now instead of hyperplanes, we're looking at these surfaces that are here by m, and or mj's rather. And the m in here is just talking about the intersections. So we're going to intersect some of the ci's for I intersect capital I, and these mj's are going to be elements from are going to be some other 0 surfaces for the indices that are not in I. So it's going to just give us the sufficient flexibility that is needed to try and draw the conclusion that is needed at the end. So, but this this upper bound somehow, this is what we used in order to do the iteration, the inductive argument for the sweep hyperplane method, and it can be done in this case as well now as an upper bound. Okay, so okay. Yeah, how do we prove this? I'm gonna try and do a drawing here, maybe. So I'm gonna put here as a set M. Maybe it looks like this. And we're gonna have these other surfaces. Maybe this is M1. And maybe we have M2 over here. And maybe have M3 over here like this. So we have the different surfaces. And so we're gonna say P is equal to 3, and we're gonna look first at the intersection of M with capital M with M1 and M2, and then see what happens when we add M3 to the mix, and what kind of behavior may happen there. So let's say that S is the set M minus the first P minus 1 MJs. So that's going to be, for this picture, I'm going to try to draw that. It's not going to be perfect, hopefully more or less good enough. So it's going to be something like this. All right. So we're gonna call this set S, and it's gonna be M, but we remove M1 and M2. And it's gonna consist of several connected components, and we're gonna know them by CJs. So maybe it's gonna be C1, C2, C3, C4, and C5. Now we want to consider one of these particular cells and see what is happening to it. Okay, so maybe consider one of the elements here, one of those connected components. Let's call it CJ, and denote by A1 to AL the connected components of CJ intersected with the last surface. So we're going to intersect that with this last surface M3 and see what happens. So maybe we consider here C4. So it's going to be, maybe this is C4, and we intersect it with, I guess I wanted to use a different surface here to make the example a little bit more interesting. So let me modify this M3 a little bit. To make it a little bit more interesting, let's say this is M3. Okay, so this is C4, we want to intersect that with M3, so that's going to look like this, right? So the intersection is going to be this part and this part. And we're going to call those elements at the intersection, or the connected components of that intersection, by A. So this is going to be maybe A1, and this is going to be A2. All right. So what the previous demo was telling us is that if we subtract a connected component from this thing, we're going to get at most 2 pieces. So if we were to subtract A1 from this C4, we get at most 2 pieces. Right? So this is the statement here in the last bullet point. So CJ subtracted A1 has no more than 2 connected components. That certainly makes sense because we will not be talking about this. And those 2 connected components, we may call them, let's say we're looking at them over here. So this without A1 would have 2 connected components that we may call here D1 and D2. And now we can ask, let's say what happens with the second, with A2, if we have one of those 2 connected components after removing A1. So since this element is disjoint from the first one, so A2 is separate from A1, then this will lie entirely either in D1 or in D2. And so let's suppose that it sits in D2, and it's going to be splitting D2 into 2 components. And it's going to have to do anything with D1. What are the implications of that? What's going to happen is that, so if we remove A1 and A2 from CJ, and we look at the connected components, those are going to be, here we have a union, this disjoint union of D1 and D2, remove A2, we get the first part is just D1 because A2 doesn't intersect D1. And for the second part, from D2 we remove A2. And from the first part D1, it has one connected component that didn't change by assumption, and D2 removing A2 is going to have at most two connected components. That's kind of the result that we had at the beginning. So overall, we're going to get at most three connected components. And if we iterate this, we're going to get something like when we remove MB, so which consists of all those A's from CJ, we get an upper bound which is equal to the number of connected components of CJ intersecting MP plus 1. Because you see here when we have two elements, we get 3, we have more and more and more, we get this total number plus 1. And then we want to go back to the object that we had in the left-hand side of the theorem, or the lemma rather, and we want to end up writing the upper bound in terms of those other connected components. Right. So this one by definition is just equal to the number of connected components of S subtracted MB. And now we look at that using all this definition and notation. So S was this set, recall, we had split it into the disjoint union of the C's, it's written there, and how's the number of connected components when we remove MB from that? Well, that's going to be the sum of the number of connected components for each of the different C's, and that's going to be bounded above, as we saw by the previous slide, this guy is bounded above by this guy, so that was kind of the conclusion from the previous calculation. And now we can think of these guys as being so because these guys are disjoint, the CJs, so we can actually consider the connected components of the union. That's essentially what we're computing. And for each of them, we're adding 1, so we can cross n. And what was this n is the total number of connected components of S, so we can write it that way. And that's, essentially that completes the discussion, gives us the expression that we wanted. So we subtract B1 surfaces, and when we subtract the next one, it is as if we were considering a set where we have subtracted those guys from the next surface. It's kind of analogous to the sweep hyperplane method that we had. Okay, then that we need to put that together with another result to obtain the final conclusion. So this is the second lemma, and the second lemma says that so the claim of the theorem will follow as a special case of the statement. The statement is saying that the number of connected components of this object is bounded above by some intersections of this sort, and the special case that we will need at the end is just that B is equal to K. So when we substitute here for little b, the case equals to K, this is the result of the theorem that we have. And one can do an induction just using the decomposition that we had in the previous slide. So the decomposition in the previous slide, we can verify that it holds, this statement certainly holds when B is equal to 0, because if B is equal to 0, we get connected components of M is upper bounded by connected components of M empty intersection over here, because B is 0, so that's just M, so of course that's true. And now if the statement for the value of D is true, and we want to do the induction step, we want to take one more element, see what happens. We actually use here the previous lemma that was giving us those that decomposition. So we insert here the decomposition, and we then see that on the one hand we have a sum that involves all the intersections that include that do not include the B plus 1 element, and on the other side we get all the intersections that do include it. And so altogether we get all the intersections of subsets up to the set. So then altogether we get the state that we wanted. Right? So that's kind of the calculation. And it's kind of nice because it's a simple argument. Notation wise, it's maybe a little bit horrible, but the intuition is relatively easy. All right, and then with this we can obtain the theorem, and which is just that the growth function is bounded above by the total number of regions in the parameter space, which in turn is bounded by this kind of Möbius inversion sort of expression in terms of the connected components of the intersections of the surfaces. And so now, since we had assumed that there exists these solutions of component bound, which tells us how many connected components we get for the intersections, we can insert that in here. So the number of connected components of any intersection of the surfaces is at most B. So we get B in here, and we still have this sum. You know, how many elements do we have of a particular cardinality? We can write it in this way and just sum over the cardinality. And then we also have the assumption that we have regular zero set intersections, and meaning that at most these surfaces intersect in an empty set. If you have more than these surfaces, we get an empty set. So you can consider here just the sum up to D, as opposed to going all the way up to the something like that. All right, so that completes the statement. Questions?
Yeah, so before the slide that had lemma 18, there was a diagram showing intersections of hyperplanes. I was wondering if there were scenarios that could lead to a compact set of connecting inputs.
What's that?
I don't remember, but it was before the 18th lemma.
And the question was if there is a compact. What?
Yeah, here. So if it's possible really to have a situation where the set of connected components is compact, or if there's anything you can say about compactness for that set.
Well, it is possible to have something compact, yes.
Does it lead to anything nice, or is it just a trivial thing?
I mean, the discussion will still apply. If you can explore that in some way. With these arguments, I don't see a way to make use of compactness beyond what we have already discussed. But maybe if you have a different strategy of proof, maybe you can use that. That's what I'm asking. All right, so then let's proceed. How is our time? Okay. So bounds for neural networks. Now we can try to instantiate this for a particular case of neural networks. And the way we can do that is that we have. Okay, maybe before that, we can just think about, okay, let's suppose we have a model or a hypothesis class that is polynomial in the parameters. That's not crazy. So you could have, for example, a deep linear network or a deep polynomial network where the parameters are mapped to the hypothesis in a polynomial fashion. And for this, we can obtain a solution set component bound, which is not terribly surprising because each of the functions is a polynomial. The zero set is kind of the set of zeros of a polynomial. We start intersecting zero sets of polynomials, and for those there are very well established results. This is one of them, a theorem by Milner and Thom, that says that, so let's say we consider P polynomials, set Fi, and each of them has degree at most D. Then we can make a statement about the common zeros of these polynomials. One is that the sum of the Betti numbers is bounded above by some quantity that depends on L and D. So D is the dimension where those polynomials are defined. So if they are defined in Rd, so we have here an expression that goes with L to the power D. All right. So it depends on the degree, and it depends on the dimension, the number of variables. Okay, so what can we say in particular? Well, what the Betti numbers, those are saying something about the number of poles in the space, something about the topology, but the zero Betti number is the number of connected components. And so, all of these guys are non-negative. So this thing in the right-hand side still is an upper bound for the number of connected components. The number of connected components is still bounded by this. And we can, for simplicity, just write here 2L to the power D. All right. So if we knew that we have a hypothesis class that is parameterized by a polynomial of a certain degree and with a certain number of parameters, then we could use this to as a solution set component bound. All right. So and if we use that, then we may obtain a result of this sort. So let's say we have a k combinations of a polynomially parameterized class. Then we can bound the growth function like this. So f is a class of functions, so that each of them is a polynomial in the parameters of degree at most L. So we have a k combination of those guys, then the growth function is bounded like this. And in particular, we obtain a bound in the BC dimension as well. Okay, so this is just by inserting the statement from the theorem that we had for this solution set component bound for the growth function. And the assumptions that we're making about the parametrization of our class. Okay, so basically multiply b times this expression in here, and we end up getting our result. Okay, other implications that are of interest here is, for example, this one. If we have a hypothesis class that consists of functions that can be computed by some type of algorithm that takes input data and parameters and returns some prediction. And it does that in at most T arithmetic operations. That could be sum, product, division on real numbers, but also comparisons conditioned on inequality signs. Then we can obtain a BC dimension bound of this sort. That is going to be expressed in terms of the number of arithmetic operations that are being conducted and the number of dimensions of the parameter space. Okay, full sketch. Maybe I'm going to skip this. Remarks. So for this last statement, one of the implications is that if you have finitely many parameters and you only allow standard arithmetic operations for computing the predictions, then this hypothesis class is going to have a finite dimension, so it's going to be learnable. Then also, if you allow only a number of parameters of computation that grows only polynomially with the input state dimension, then the BC dimension also only grows polynomially with n. And in turn, the sample complexity will also only grow polynomially. This result is no longer true if you allow other types of activation functions, or other types of operations, like a sign function or floor function, so which is different from taking a sum or taking a product. And for those, turns out that the BC dimension can end up becoming infinity.
How do you do products and additions if your target is binary? You do binary like 1 plus 1 is 0?
No, we're just making this binary at the very end.
Oh, okay.
So you compute a real valued function. So that's the way we define this kind of signs of combinations. Combinations of signs of functions. So yeah, you compute a real valued function and then you take the sign just to predict the class. Yeah. So so that was an upper bound, and one can actually obtain also lower bounds, so that the total result ends up being optimal up to constant factors. So if you have a class that is parameterized by the real values and can be computed in a certain time, then so you can find a class that has at least a BC dimension of d times t. Excuse me. So it's an existent statement. It doesn't mean that every class that can be computed in time t has the parameters that responds that. So it's just there is one class that does that. All right, so proof, I'm going to skip through that. And so, of course, some of the cases that are going to be most interesting to think about are maybe neural networks with piecewise polynomial activation functions, because and they're gonna have a piecewise polynomial parametrization as well. And so you can estimate Taylor's dimension for different components of the parameter space. You can take the parameter space, split it into the pieces where the parameterization is polynomial, and for each of those pieces, use the bound that we had to estimate the growth function of this dimension, and just add everything together to get the final result. And so, this could be one example. So I work with piecewise coordinate activations. Let's say you have neural network with a certain number of parameters and a certain number of computational units, and each of the computational unit has a piecewise polynomial activation with the ReLU. Let's say with p pieces and a certain degree. Let's say the degree is bounded by L, and then the output is a linear threshold unit. This is when we make it binary, just like the output. Then the class of functions that we have satisfies this bound for this dimension. We can also obtain a result here for the log function. So in this case, W plus WKL log P. W is the number of parameters. Here is the number of computational units. P is the number of pieces of the activation, and L is the degree. All right, so the proof is, maybe just maybe we're gonna go through it now. It's using the discussion that we had. This statement can be improved if one wants to make a complete use of the architecture of the network. If you want to say something about the particular structure of the network, let's say the network has n layers. It's a deep neural network. Then one can do this a little bit more accurately by using a more explicit computation of the argument that I told you. Partition the parameter space into the pieces where the parameterization is good or polynomial, and for each of them you can shape the bound of the sort that we have for using a solution set component bound, etc. One can obtain a result of this sort that is depending on the specific architecture of the network and the depth. So it looks like this, and it goes with W times n of W, etc. Okay, I think I'm going to stop here then.